on the computer. Okay. Should work. I don't have the, to be sure, let me see again. Okay, it seems to work. Well, as you have seen in the video clip, the introduction video clip, in which I suggested to you to watch some internet links, some YouTube links. The YouTube links I suggest you to see are important. So please do. In particular, one that we didn't see in the video clip is the Mark Reiber conference with the robot. Maybe you have seen it, because not only show the top of the technology in legged robots, but also the philosophy of the design of a robot, in which algorithms, mechanics, design, organization, integration of software components on are a whole. They cannot be separated, and that's the real important concept. Of course, robotics is not only legged robot or mobile robots or automated manufactured robots like industrial robots that you have seen. There are also drones, of course, aerial vehicles, or ships, or any kind of or space robots and so on. But in general, the idea is that there are always many things to put together. In particular, the software. We are talking about the software. In the introductory video clip, I've shown you that we are talking about the low level. Low level software development, low level programming. The level that we have related to the C language programs, the procedural programming. And this is ARP. And similarly, the real-time course. At the highest level, there is the software engineering. The course in the next semester will be so far, software architecture for robotics. But starting from this semester, but also in the second, you will have also a course, lab course dedicated to, well, not here, dedicated to ROS, the middleware. So in these slides, we will see some concepts that are so general and abstract, but it's important to declare which are the definitions of how to build a software architecture for a robot, beginning from the highest level. That is level in particular that is used by ROS, middleware, so more abstract, and even at a higher level by the software course. So, well, let's skip this because I want to arrive to the break as soon as possible. We will start from this example. Why from this example? Because the assignment that I don't know if today I will be able to do, but surely tomorrow, the assignment, so the homework for you is just to work on this, on this model. This is a simple model of an autonomous mobile robot. Typically is a mobile robot with wheels and able to go around. If you have seen the the video clips, the prototype of every autonomous mobile robot is the Shekey experiment, the Shekey prototype in 1972. But 1972 is the year of in which the project reached those results, but the project started in 1966, so it's very old. But the architecture is still the same, as competence over what? On user interface. So a user says to Shekey or to the robot in the Barillas warehouse to displace palletized things in the other video clip. A user supervisor says, well, go there and do something. In the Shekey word, it was go there and push that object. So the system, so the user interface is a component, a software component, because is a sort of, not as a software, generally is a GUI, is a graphic user interface. You dialogue with the robot. Then there is something inside the system that is able to decide which is the path. So it's a component, it's a software component interfaced with the user interface that decides which is the path. Not, in general, is not a straight line, because the system knows that there are the map with obstacles and so on. So here, somewhere, there should be a map. That is a system data structure. On the contrary, the path planner, the user interface are software modules. Other software module would better use another color, because but it's a bad drawing, but there is a special file in your in our web with the complete drawing of this kind. And the collision avoidance is an important software modules which keeps the robot far from obstacles and avoids obstacles. But sometimes there are also a more complex system, and usually, not sometimes. For a rule, a legal rule, there is also a module that is more important than collision avoidance, that is emergency. Collision avoidance tells the path planner that the path has to be some shape to avoid obstacles, but in case something happens unexpected, or the emergency should stop immediately the robot, and is another module, another software component. Localization is another software component that takes into account all information coming from the sensors and sensors like video cameras, or like it happens more frequently in industrial robots, laser scanners, but also other sources of information like GPS, or the whole family of GPS systems. And then there is something that drives the motors and has information from the motors, from the drivers of the wheel, and reconstruct the displacement of the robot just to update the map. So it's a series of complex modules interfaced with the communication system. So this is just an example, but just to get inside the terminology and to be prepared to what we will see in a short time. This is another example of the components of the software algorithms, and arrows in general try to capture which is the need of sending and receiving data, so the communication issue. So communication is the first important thing, probably the most important thing in a complex system like in a robot software architecture composed by many components. And communication, we must know which are the definition of the basic, the classification of communication methods. One is message-based. Message-based is any system in which one component is connected, well, here, is connected to the other component to which there is an arrow here, but can be an arrow here, or both arrows, so that communication can be two sides. And communication normally as a message with a content, in that case variables. The second way, low level, this is the lowest level of classification of communication system, lowest level. Or you transfer directly data, or you use a common area just to share data. In this case, you have only one place, one piece of memory, one place in which data are written, and the two components that want to communicate, or more than two, just read and write. These are the two basics. No other, at the lowest level, no other mechanism or primitive exists. Can have some variation. For example, message can be sent and received also to C. So there can be one source and several destinations, and in that case, this is typical of the shared memory. Typical, and you will see in this course and in the real-time course which are the consequences and the primitives that we need in writing code, because we need some special primitives. In that, this is the case for those of you who already know that using the concept, the primitive that's called thread programming, and thread programming requires primitives for having safe and secure sharing. It is not simple to do that. This is a way of sending and receiving data that are used in most of every programming language, but needs many primitives that usually are offered or by the operating system itself. We will call them system calls. The system calls are typical of this, for this method of communication, and thread programming is typical of this. But we must now abstract the four high level or they're not high level, they're mid-level principle of communication. Based on implemented using the shared memory or messages. Push is one-way communication, sends the data as directly. So the producer, anytime the producer wants to send the data sends immediately. It's similar to the notifying something that is very common using the smartphones and the web and so on. So pushes. Another, probably more common in programming, is pulling, as to say, the consumer asks data from the producer. So the producer is not able to send data anytime, but just upon a request. You will see that this is basically a mechanism used for urgent data, emergency data, for example, some data that can be can have an immediate effect. P cannot wait for C to ask for data. So these are typically at the lowest electronic level. This is the principle of interrupt. But there are also software interrupts, and we will see they are called events, and you send a signal or an event. Pull is typical of the synchronous communication in which the two are aware of the fact that the consumer wants to know something. This is a very useful and common in paradigms, not only robotics, of course. The idea is that there is one producer of data at many consumers, but consumers can subscribe and unsubscribe. So at a certain time, for example, P, suppose there is an example after, I think it's, no, well, we'll skip. Laser rangefinder. Laser rangefinder is a device very useful, very common in mobile robots, in which the laser scans the environment and gives the software the distance at for any direction of the beam in which there is an obstacle. So the laser scanner, laser rangefinder usually works autonomously. So, for example, scans 180 degrees 10 times a second, for example, continuously, like that. Does that. And the laser rangefinder is a publisher of data. So the laser, in this case, P is a laser rangefinder, and simply says, okay, 10 times a second, I will send a vector with all obstacles I've seen. Who is interested in that? In that case, many components of the system for the emergency component, the graphic user interface, for example, because if the supervisor wants to know what the robot is seeing anytime, probably needs to know what the laser perceives, but also the maps builder and the maps maintainer, so the updater, the software components that continuously update the map and put the obstacle that is perceived. So they subscribe and receive data. The idea is that from time to time, one of those components, maybe a lot, can subscribe or unsubscribe. If the component unsubscribes, it lessen the load of the system because there are less communication involved. And so dynamically you can subscribe and unsubscribe. This is so useful and common. That is one of the primitive that we will not see, because the lower level of programming that we will see, the POSIX standard, does not have such a primitive. That is a higher, must be, and we will see how, must be built on the lowest level POSIX primitives. Finally, but for example, not only for example, but is important in ROS, in the middleware that you will learn, publish and subscribe is one of the most important primitives for making communicate all the components. And publish to a blackboard. Publish to a blackboard is similar, is clearly related to the idea of blackboard, so a common area. The producer sends data to a blackboard. You are talking, some of you want to ask a question or no, just
yes,
no?
if he sends data to B, background way consumes.
Pardon? Can you repeat? Okay, I go on because I'm finishing this part. Another possible idea is that the publisher just writes data on a blackboard or whiteboard. Every component can read, when needed, data from that. This is an example, and I think now we can, for 5 minutes, stop. And I want that you understand exactly this terminology and these principles, because we will use them widely, not only we. And the document is on our web, so you can see that. If you're okay, I can leave you alone for 5 minutes. I keep
Yes,
it open so you can talk each
Okay.
other if you want.
Okay.
Okay, 5 minutes break just to take a coffee. Oh, I'll stop recording. Okay, recording again. Share screen. Now I will show you directly this simple example, because is exactly the simple example in more details respect what I did before. Let me take another file, not this one, the one I published on the in our web. Well, this annotated file, very roughly annotated, as a M, that means a module. Module is a software component, a software algorithm, a program, if you prefer. Separate from the other modules, because the idea, as I told you in the introduction video clip, is that a robot program is composed by many programs working in parallel or concurrently. Each one of them is a module. Normally it's called module, is the typical ROS terminology. And the problem is how to define which is the algorithm of the module, which are the data used by those models, and which are the interfaces, the communication interfaces. But there are also system components. Roughly, I've written here S as a system component. System components are interfaces towards the hardware devices. For example, the laser rangefinder is not.
Sorry, Professor.
Yeah.
I see the folder and not the presentation. Is that's right? Or
Yes, Professor, we are not able to see.
Sorry. I have to do something else.
thank you.
Sorry. Well, okay.
No problem.
As soon as the classes go on, I hope that will be more clever than now, or less dumb than now. So there are also components, system components. Usually is the interfaces toward the hardware that is in use. For example, in that case, two, because localization and collision avoidance need sensors to measure which is the free space in the environment and so on. And also the base interface, that is the mechanics and the controller, the hardware controllers of the wheels, of the motors and the wheels, are components which can be, to which send information, in particular to send them set point for the speed of the rotation of the wheels, for example, and to read positions. So in this example, you can locate which is the organization of components. Let me go back to I want to share the screen with oh, this one, okay. Can you see the Aula web page?
Yes, we can.
Yes.
Okay.
Yeah.
Here there is so in general, this is a real scheme of a system of an AGV, so mobile robot that carries a manipulator on top, in which you see there are many components detailed with the kind of communication and some other specification regarding, for example, the speed of the cycle timing and so on. So this is absolutely a general way of designing the software. Well, in our case, the case I want that you expand for the next week, but tomorrow we will work again on this. consider these are the system components. You will see in our web, there are system of drawings. This is the typical controller for a motor. Usually a mobile robot has more than one motor, at least two, but sometimes three, including a steering, or two wheels, two independent wheels. And is a component, is a motor controller that receives data that I call set speed revolution per second, and the delta rotation can be read. Delta rotation may be simply the displacement, rotational displacement just after the previous readings. So you can read many times and you have the delta, so the incremental rotation. The laser range finder is a device which produces data. It can be read somehow for typically, for example, 10 per second, and it gives you back a distance vector. So the laser scanners works in this way, scans, for example, 180 degrees, and this is the vector. How many? An industrial laser rangefinder gives you 2 or 3 samples per degree. Some accurate rangefinder can give you more, like 1/10 of degree, 1/10 of degree. It doesn't matter. In any case, for any scan, every scan, and I've written here 10 scans per second, there is a vector of 180 points or 180 values of distance or more. It depends on the accuracy of scanning. Other component for our homework are GPS. This probably is not a real GPS, not based on satellites, but on a local system. But the philosophy is the same. Autonomously, for example, 1 time per second or maybe more, it gives you the absolute position. This is an absolute position. Emergency device is a device that can take into account several sensors, for example, touch sensors, on-off laser or proximity sensors, and simply gives you back a Boolean, well, there is a mistypo, this should be stop or free, that says, okay, if the Boolean value is stop, the robot must stop for safety. Otherwise, is free to go on. Modules. Modules are in general programs or algorithms or tasks, as you can. The idea is that they are independent and concurrent. User interface that is connected to the user supervisor. The motion planner is able, basing on the map and on the constraints and on the goal that the user issues, is able to decide a trajectory. There will be a map, we will see, there is a common data structure shared by many other user modules, and there will be some module who updates continuously the map and carries out the localization that is based on algorithm based on the distance between with known obstacles with GPS and so on, and the motion controller. The motion is uh, the control loop, typical of the technologies of controlling and servoing a motor, but is also able, as we have seen, to give back the how the wheels are rotating. And in general, there should be a geometrical called kinematic engine that carries out all the computation for transferring, for example, rotation of the wheels in absolute positions of the robot, or translating distance from known obstacle to absolute position of the robot, and so on. So it's a geometrical engine, kinematic in the sense that, as you will see in the one of the robotic courses for simulation and control, all this computation is of kinematic type. And then a software module dedicated to emergencies of any kind, including failures of the controllers, for example. Anything may be dangerous, requires stop and an alarm to the supervisor. Well,
excuse me.
Pardon?
Sorry, Marco Fedotti here. So if I understood correctly, system components are what interfaces hardware to the upper level, let's say, while modules are what connect all this data sampled from the interfaces in a kind of way.
Correct. System components are hardware with the low-level device driver, so that they are virtualized and can be seen by a source of data, and they can use data, making some changes in rotation of the wheels, for example. Okay. Did I answer? Okay.
Thanks. Yes.
Okay.
Thanks.
And then just a look at the system structures, data structures, not the system structures, so data structures. Well, the most important data structure is the space map. So it's a map in which there is the environment, the robot itself, and all abstract information. For example, if an object is soft or hard, or can be hit or not, can be moved, like in the shaky experiment, and which are the goals issued by the user, and so environment, obstacle, robot. So it's a representation, sort of simulative representation of the world in which a robot operates. This is typical of any robot, not only mobile robot. In a mobile robot, it's simpler and clear. It's just the two-dimensional map in which the robot acts. And it must be continuously updated by a software module that takes into account the movement of the robot to position correctly the robot in the proper point of the map, which takes into account all information coming from sensor for localization, of course, and even if there are obstacles or other things that move by themselves, because the environment in which a robot moves needs not to be completely static. Maybe may have some independent obstacles or other robots that move, like in the warehouse we have seen. So this was just to show you how to start organizing the several parts of the software of the robot, putting together the devices that are abstract as structures, the data, relevant data areas to be managed, and all software modules or algorithms that must be further or more deeply characterized regarding the speed, the accuracy, and all the communication between them. So if we go back to the, I think I still have. This, okay, this is the reason why we have this boring discussion about the way in which system modules have communication with each other, because probably we will soon face that problem at a low level. As I told you, not all those primitives are available in a low-level programming that we call the POSIX standard. For example, the most popular that is publish subscribe is not given, but can be in some way implemented. But and you will also see how the higher level and more abstract primitive like publish subscribe can be implemented in those in the low level. So I don't what I have to say. Well, some other clues, not so important and not related to the assignment, so not to your homework in a sense. And homework is just for going deeper in the discussion of these items after you have done something. So you have discussed modules, data log. Just to point out, the data log, or while logging data. This set of slides has a lot of blank sheets of paper like this, while logging data, because of the full sets of slides and also some answers. I will publish also the answer, but after tomorrow. So if in the meantime you answer by yourself to to all these questions, I think it's a good idea. So think of it. Why logging data? Log data means that you have data that recording what is happening in the system. Every robot of any complexity have a log. It's very, very important, but not only robot have, also software with pure software have log data, but in robotics is absolutely compulsory. Why that? Because all experiments with a real robot are in real time and are costly, time expensive, and so on. And correspond to the running of a concurrent program, in which is very difficult to find which is the source of error. So the only thing we have to do, the first thing we have to do is just to log data into a file. There are many ways of doing that. And we will see also in the POSIX system calls that there is always the possibility of extracting the information about an error that can occur, because errors sometimes are not dependent from the logics, but from the time sequences of the time situation in which some instruction of the program is run. Is different from normal programming, in which you follow the logic, and if you are able to understand exactly what every statement does, you finally you will find the error if there is an error. In concurrent programming, this is not true because the performance or behavior of the whole program composed by several programs together depends not only by the logics of the algorithm of every single program, but also depends on the time instant in which they communicate, with they interact. So there are infinite ways of making a program to fail due to the timings. You should foresee everything. You have instruments to prevent this kind of errors, but they always happen. And the only way, when you have read 100 times the code and you still have the error, is to examine the log. So every component of the software architecture should write a log file, write on a log file. This is just a picture of a real log file, and you see that usually we need also an algorithm or a user interface to browse the log file to understand what it means. Log files sometimes can drive a simulator, and so you see in real time what is happening. The choice of the relevant data to be written is just a sort of artistic or experience decision, because if you have too many data, the system becomes slow and you use a lot of disk to store data. You have too little amount of data, you may not capture exactly when they are occurred. You will see that in POSIX there are primitives exactly for trying to capture the errors and so to report on a log.
Sorry, Professor.
Yeah?
May I interrupt you?
Yeah.
Marco Fedotti here. I saw in the slide it talked about transparent logging. What do we mean with transparent in this instance?
The transparent logging means that you can use a simulator to feed the simulator with the transparent logging, so that if the simulator is fed by real data during the robot is acting, you see no difference. Is very important, in particular in space robotics, in which you have while you move, or underwater robotics, or robots working in a dangerous situation in which you cannot stay near the robot. So usually in the user interface you have you watch a simulator of the robot, so not the robot itself, and the simulator is linked to the robot using the connection of data. And if you log those data, all the data that drive the simulator, you have a big log, but in any case you can play back a real execution like you were just watching it really online.
Okay, thank you.
It's just an example. So robotics has a lot of separate issues and requirements. In particular, it is clearly different having a robot acting on the surface of the planet Mars and a robot on a warehouse displacing things. For a robot in the a rover, planet rover, like ExoMars and so on, the time lag between for the communication is such you cannot teleoperate the robot, but you won't see what the robot does. So you need a log that is able to reproduce in simulation after tenths of seconds what did happen. The coordinate frames is a funny argument. I'll let you read this item, because it shows that it's a funny thing, but really important. So as to say, if you use meter, please use always meter and not inches or yards and so on. This also for the angular weights and everything. Simulation is really important in robotics, really absolutely important. As a demonstration, the ROS system was built as both a middleware to write a robot program and the simulator. So the simulator is in a sense embedded in the ROS system, because experiments used with the robots or debugging a robot is so costly and so time consuming and so complex that if you can debug or test a system as much as you can in simulation is really important. So simulation is a key issue, even if sometimes, and this also happens in many theses, master theses, experiments are made too much in simulation, thinking that it is enough, but in the end, you need to test your system on a real robot after you have made many random simulation. Software architecture, as you've seen the whole structure from a distance, and use techniques that you will see in the second semester. And well, as for programming, I close here this because programming, just one information. This course has no particular prerequisites about knowledge regarding programming. Well, it has, and they are written in the course description that you have seen, and hope that you have seen in the main page of in our web. So you will use C language programming, because the POSIX standard is a set of libraries whose principles and whose primitives and so on can be completely understood using C, procedural language C in particular. No problems if you prefer to use C++, can be interfaced also in Python or Java. So it doesn't matter. It's just a different interface. But the lowest level of programming language is C, and I will use C language all over the course, no other language. But I assume that you are able to program in C language. If you don't, take some recover strategy, get in touch with us, with Professor Masso Giovanni, with me, with some other teacher, and we will provide you some suggestion or some online courses to arrive to the threshold level that is very low, so it is not. I just anticipate that there will be a questionnaire, not in this course, probably in the Emaro first year course, a questionnaire for asking you your knowledge about programming languages and maybe some other things. So it's a questionnaire just to make us to organize correctly the course, and also if there are some weaknesses in programming languages, in particular for ROS. ROS as an interface to C language, but is more cluttered and complicated than the normal interface in C++. So for using ROS, there is today is a standard not only in the EMARO, GEMARO courses, but all over the world, and also in industry. So the ROS is something that you absolutely have to know. The ROS will be taught using the C++ interface. And very soon, probably this week, there will be this questionnaire, and I ask you to answer smoothly, clearly, with no, so honestly. So there's, we don't know if you are able to do the questionnaire in our web anonymous, but the problem is not to know what the single level of the students, but just to organize as in the best way the course. So I have anticipated, which is the assignment, which is the idea of organizing. You will find in our web, I think I have, in our web, here. Okay, the to-do list. The to-do list is a long, since probably we will jump over the next week, because on next Tuesday, as I told you, we have no class, but Professor Mastro Giovanni will talk about the whole course. So this is for 2 weeks, but we will get inside all tomorrow. One is internet search. So is something that I want you to do, I suggest you to do strongly, and similarly to what I did in selecting some YouTube clips regarding robotics, find significant mobile robot, in particular the UAV is an acronym for unmanned autonomous vehicle, that is mobile robot. Industry and research. Since I want that you start designing the software system and you will for the mobile robot, and we will use the design that you do as long as we will learn primitives for making all modules to communicate in POSIX. Then try also, while you have a look to those, you not necessarily look at the clips, video clips, but also home pages with describing, you will find many, absolutely tens of UAV. Trying to understand which are the differences in the geometric structures. There are steerings, how many wheels, and so on. Then the system, the subsystem, the other subsystem, that the one we have addressed some minutes ago, motor controllers or servos, laser range finder, the most popular in industrial industrial mobile robots is called SICK. I don't write, it's just, otherwise it's sort of advertising. It's a commercial trademark. SICK is written exactly like sickness, the word sick, when someone is sick. Hope not for the COVID-19, but sick. SICK is the lead manufacturer of rangefinders, and system for emergency stop, GPS, computer and memory. So those components that we will use in our homework. Well, dialogue elements, well, I think we can not consider this. This is the user interface, the kind of user interface. Well, don't think much of it. And then as a further step, create a software architecture scheme based on the subsystem. The software, the scheme based on putting together, linking together all the drawings that I have shown before in the other, like this one, no, this is a to-do list, and so on. And trying to put the kind of communication primitive, selecting the communication primitive inside the set of communication primitives that we have discussed. So send data, subscribe, and so on. Okay, this is the relevant point in the assignment that I want you to think of. Okay, I stopped the share, and now I do a strange thing. It's not so important now, but I will put you in how many more? In small groups. Small groups about, well, 6, 7 students, randomly chosen. So please introduce yourself to the other students in the group. Probably that group will never be a group again if we, in successive classes. It's just an happening. Please discuss and also talk together about the course, and if all is clear or if there's something to ask and so on. Okay? I will do this with the technique of the breakout rooms, and just for 10 minutes until 4 to 5, okay? Because at the end we will meet again in the class, in the classroom, in the common classroom. We will see if there are questions or something like that, and we will say goodbye until tomorrow. So I will the breakout room. You will be asked to accept to stay in a separate room. All rooms are separated, so people in the breakout room can communicate each other. It's a small Zoom meeting. You can also share the screen if you want by in the group, not common. I think I will not. I can jump in every group one at a time if I want. I don't know. It's a technique that I will use in the final exam. And then at the end, I will ask you to exit from the breakout room, from the local room, and we go back to the common room. I stop the recording.